today, so this is the last lecture, and I posted already the slides yesterday to on Teams, and the second to last page on my slides gives you instructions how to do the final exam. So there are a couple of problems that you have to go and retrieve from the web page of the book. I will show you when I come there, and I'm asking you to complete some of the exercises that we have posted to the book site, and so this will be a sort of a pass-fail grading. So I'm not going all through the details in my grading, but so let's say if you have done reasonable job, so that I see that there is a serious effort to try to solve the problems, and the report is understandable and done with certain level of criteria, so then I'm happy to consider it pass. And so I will give you the details when we come there, so we can go through also the web page so that you see what I'm asking you to do. All right, so I'll start sharing the screen again. Let me go to this page. I think here we go. So today I was not quite sure last time what we are going to go through here, because I wasn't sure what sort of material I will be able to go through this time, but it looks like I'm going to stick to the tree-based methods today, so I'm not opening a new topic. I believe that this is better, so it sort of makes it more consistent end for this course. And so what we have been talking in the last two lectures, hours of the lecture, was the classification tree. And remember, the classification tree was the algorithm. When you build it, it contains two steps. So first you grow the tree. So you grow the maximal tree, and so then this tree typically has lots of leaves. And it is very clumsy and also somewhat insecure, because it is sort of fitting the tree to the data, and data is always noisy. So it is doing basically an overfitting. And so you don't want to do overfitting to noisy data. So therefore, it is advisable to not use the maximal tree for classification, but you use a smaller tree. And smaller tree is obtained by pruning. So you go through all the nodes which are not leaves, and you see what happens if you cut the branches that are below that node that you have chosen. So you are looking at the so-called cost complexity function. So cost complexity function was a linear combination of the misclassification error that the tree is doing if you use it for classification, and this is of course in terms of the training data, and the complexity, which is simply the number of leaves in the tree. And so you are sort of trying to find a nice balance between those two. And so there was an unknown parameter alpha, which was the weight that it defines which sort of weight you give to the complexity. And so the strategy was that you go through all the nodes which are not leaves, and you find the critical value for alpha for each node, meaning that the critical value is the value of alpha that makes the smaller tree better than the larger tree if you prune. And so now you choose the smallest of those alphas and you prune there, and then you continue. So the idea is that you are trying to do the pruning in smallest possible steps. So you're pruning the smallest possible part of the tree away. Smallest meaning that you are hurting as little as possible the cost complexity. So that was the idea. And so this is kind of an easy thing to say, but of course there are lots of technical details that we have been trying to address in the book. So if you have the book, you will see there are also some snippets of MATLAB code which are pretty easy to translate also in Python or other languages, are to see how this pruning can be done using structures. So structure and structure arrays. So you can think that this node is a structure. So it is like a spreadsheet, and each node contains the information: who is the left and right offspring. So where do you go if you decide to go to the left or to the right? There is also the splitting criterion. So there is the splitting index and splitting value. So you know which attribute you have to look at, and then what value decides whether you go to the left or to the right. Okay, and so then it also gives you the information about which data points are in the rectangle that defines that node. Because if you are going to use that node for classification, you need to know which one is the winning class, and because the winning class is deciding how you classify. So that was the information that this node has to contain. So this is still a little bit obscure from the point of view of pruning, because you need to have a strategy how to simplify the structure when you're pruning. And so I'm showing you first something which is useful for the pruning process, and so then we go to regression trees, which is a fun topic. So where we are approximating functions by trees. So suppose you have a tree which I denote here by R, and so R contains nodes R1, R2, etc., Rm. So you can think that you have a tree with M nodes, so R1 to Rm. And each one of these nodes, if you take one of these RMs, there should be hidden somehow the information of who the offsprings are, so that you know the tree structure, and also you know what the split value and the optimal split attribute is. So if you think about the pruning process, so you choose one of these nodes, and then you need to take away all the rectangles or nodes which are below that particular node that you are choosing. So it is quite natural to define something which is called successor matrix. So successor matrix is an m by m matrix. So m here refers to the number of nodes in your tree, and the successor matrix is such that the element kj is 1 if and only if rj node is a child of rk. So you see, if you have rk, which is one of the nodes, the node has two children if it's not a leaf. I mean, either it has two children because this is a binary tree, so there's the left and right offspring, or there are no offsprings when this rk is a leaf. And so there are two nodes which are offsprings of maximum two nodes which are offsprings of this kth node, and in AKJ you have ones in those columns that have the index j, which is pointing to the offsprings. So if you want to know who the children, the left and right children of RK is, you go to the kth row of A and you pick the two columns which have ones in them, and you know that those are the nodes where you can arrive to by asking the yes or no question or left and right question in that node RK. So if you pick any row from your matrix A, there are either two ones and other components are 0, or there are only zeros in the row, and the only zeros row indicates that your RK is a leaf. So the kth row indicates the nodes that you can reach by taking one step down in the tree structure. So this is how the successor matrix looks like. Now, since we are planning to remove not only the children of a node when we are doing pruning, we want to also remove all the children of the children, so grandchildren, etc. So we need a little bit more, and so then we use a little bit of results from graph theory, And the results that is not that difficult to figure out why it is so, is saying that if you ask which nodes I can reach taking 2 steps down in the tree structure. So 1 step takes you to the left and right child. Now you ask how many, so which nodes of the tree I can reach by taking 2 steps down. So you go 1 down, let's say to the left, and then 1 down to the right. And so now you ask which nodes did you reach? And it is not so difficult to show that if you take the matrix A squared, so A, remember, is a square matrix, and A squared is just the matrix product A by A. And so if you calculate this A by A matrix, and I will show you an example soon so that you see how this works. You take this A squared matrix, and then you look at the kjth entry. And if the kjth entry is 1, then you know that you can walk from the node Rk to the node Rj by taking 2 steps down the tree structure. So you go either to the left or right child first, and then you go to the left or right child first, and so second, and so then you arrive to the jth node. And more generally, if you go down the tree, let's say L steps, L layers, and you ask which nodes can I reach by taking L steps, you take the Lth power of this successor matrix, and then you look at the kth row, and wherever you find a 1, you know that node can be reached by L steps from Rk. So this is a general principle in graph theory. If you have this sort of a matrix that tells you where you can move by 1 step, so then if you want to ask how many, which nodes you can reach by L steps, you take the Lth power of that matrix. And so since we know that this tree has finite depth, so there are not infinitely many steps that you can take, because if you take enough steps, you arrive at the end, you arrive to a leaf, and after the leaf you cannot go anywhere. So this tree structure is such that we always go downwards, not upwards. Okay, so therefore you know that at some number of steps, some L, you always arrive to a leaf, and after a leaf you cannot go anywhere. So that in terms of the powers of the successor matrix means that the L plus 1 first power of A has to be a 0 matrix. And when you get 0, you know that you have reached the leaf level, and so there are no more successors for the leaves. So at the end, you just keep calculating the powers of L, and your tree may be huge, so the L is large, but at the end you will end up to the situation that L plus 1 is 0, and then you can stop. Of course, after that, all the exponents of A will be 0 matrices. Okay, so this is the idea, and so then now you can ask the following question: given a node, which ones are the nodes that are below that particular node? So if you think this question, that means that you are asking which nodes you can reach in finite steps if you go through this left-right tree structure. Okay, so the children you can reach by 1 step, so that's A. The grandchildren you can reach by A squared, etc. So you go all the way to AL, which is the last non-zero exponent of this matrix, and you sum them up. And so what does it mean? It means that if you go to the kth row of this G matrix, which I call genealogy matrix, then this genealogy matrix has the nice property that if you have ones in those columns that correspond to leaves that you can, the nodes in the tree that you can reach from Rk in a finite number of steps, and the finite number is always less or equal to L. So that's a genealogy matrix. So genealogy matrix simply tells you which nodes are below your chosen node. And so when you do the pruning, of course, when you're cutting at one node, so you want to remove all the nodes which are below that node that you have chosen. And so what you do, you take the genealogy matrix and you go to the kth row of that genealogy matrix, and there indeed you can read all the nodes that you need to remove, because those are the nodes which are successors of Rk. So this GKJ tells you that if you just branch through the tree, you arrive to one of the let's say leaves at the end, which are below that at Rj. But you are also in this G listing all the nodes which are not leaves, but which are under your node that you have chosen, the kth node. Okay, so here is an example so that you see how this works. So I have chosen a very simple tree. So there are 5 nodes. So therefore my successor matrix is a 5 by 5 matrix. And now let's see. First we start with the successor matrix. So R1, we take the first row of this matrix A. And looking at the tree, you see that you can arrive by one step to R2 and R3. So I put 1 and 1 in the second and third column, and the others are 0. So each row has at maximum 2 1s and otherwise 0. Let's go to R2. R2 is a leaf, so there are no successors, so there are no nodes that you can reach from R2. So therefore I put a row of zeros here. There are no successors in R2. R3 has 2 successors, 4 and 5, so I go to the third row and I put 1 in 4 and 5 because those are the successors. And then R4 and R5 are both leaves. There are no successors, so I put 0 rows. So this is the successor matrix corresponding to this tree. So you see how simple it is, and it's very simple to construct too. So you're just reading who the successors are. So now let's look at the matrix A squared. And before I do that, let's try to figure out what it should look like. So if you take 2 steps down in this tree, the only way that you arrive somewhere by 2 steps is that you start from R1, you go to R3, and then to R4 and R5. From R2 you cannot go down. From R3 you can go down, but not 2 steps. So there are no way you could go down 2 steps from R3, and the same R4, R5. So therefore what I'm expecting to see is that if I take A squared, I get a matrix which has non-zeros only in one single row, which is the first row. And indeed, if you do this, you see that A2 is A squared is 0, 0, 0, 1, 1. That tells me that if I take 2 steps down from my first node, I either arrive to R4 or R5, and from other nodes you don't arrive anywhere. So you see that there are zeros here. So there's no way you can reach anything by 2 steps, and there are no way to get anywhere by 3 steps, so that the tree is not deep enough to allow 3 steps. So therefore I know that in this case A3 must be 0. A is A cubed, so it's A to the power 3, and so is all the other powers. So my tree is that simple. I only have the A and A squared, which are non-zero, and all the rest are zeros. And so then if I put together the genealogy matrix, I take A plus A squared. And so now if you look at this A squared and my A, which is here, you're summing them up. So you see that the first row is 0, 1, 1, 1, 1, then a row of zeros and 0, 0, 1, 1. And those are the non-zero entries. So what does this G tell me? It tells me that from the first node, I can reach nodes 2, 3, 4, and 5. Well, that's natural because my first node is a root. From node 2, I don't go anywhere, so it means that it's a leaf. From node 3, I can go to 4 and 5, and that's it. And the 4 and 5 leaves are no. So this G tells you exactly who is below who. So if I'm asking who is below the first node, reading the first row tells you everybody is under the first node. Who is under R3, 4, and 5, and so on. So the genealogy matrix tells you exactly that if you are going to prune this tree, let's say from R3, it tells you exactly which nodes you are going to lose. You're going to lose 4 and 5 because that's where you have the ones here. And so this genealogy matrix is something that really helps you to do the pruning. So the tree pruning is best done. So when you have the tree, just set up the what is it called, this A matrix, so the successor matrix, and so then calculate the powers of successor matrices, when you start to get zeros, you know that you have to stop, and then you are summing all those exponents to get the genealogy matrix. Now, if you want to prune from Rj, so when you do this testing, how the tree is performing in terms of the cost complexity, you choose one node, then you read which nodes are under it by reading the column, the jth row from your genealogy matrix, and you remove all those nodes, and that's your new tree. Now, of course, once you do that, if you decide to use this tree, you have to update your successor matrix. Well, this is simple, because if you think about the successor matrix, you just delete the rows and columns that you just removed, because they are no longer in the tree, but everything else is in the tree. And so therefore, when you're removing the rows of K1 to KL, you're removing everything that is below the nodes that you have taken out. And of course, the columns need to be taken out because you cannot reach any longer those nodes. So there is a very clear logic why the successor matrix is updated simply by deleting the rows and columns that correspond to the nodes that you just removed. And so this genealogy matrix makes the pruning rather simple. It is still a little bit of a bookkeeping problem. So these three methods, they require a little bit of bookkeeping because you have many levels of quantities here. So you have trees, you have nodes, and you have the quantities that are related to those nodes. But it's only an indexing problem, and but this genealogy matrix is certainly something that you should bear in mind when you do the pruning. So it is really a handy tool, and so a little bit of this bookkeeping is then explained in MATLAB code form in the book. So I'm not going. That's rather technical, and when you see it, you say, of course. But so I leave it for you to figure out how you do it, because there are some numbering issues that you need to bear in mind. So because let me explain what the numbering issue is. So if you are numbering the nodes, and then you're deleting. Well, let's go back here. So suppose well, this is not a good example because here it's pretty obvious. But so let me explain. So if you have a tree and you are deleting a node and all the nodes below that node, so if you're deleting all the nodes below one node, you may end up having nodes in your pruned tree where the numbering of the nodes has gaps. So you may have, after you have pruned the tree, you may have a tree where the nodes are called R1, R2, R7, R8, R9. So because you have removed the nodes from 3 to 6, and so you want to do a renumbering so that the numbering of the nodes is logical in your tree. So that's the bookkeeping issue, but it's kind of obvious what you need to do. So you have local numbering and you have global numbering. So this is obviously simply a numbering issue, but it's sometimes may be confusing and may cause some problems when you do it incorrectly. Okay, so rather than going into the numbering issues of the nodes, I will go to another topic, which is the tree regression. So tree regression means that we are making us, in sense of statistics, we are doing an approximation of a function which is partially known. So suppose in one dimension. So one dimension is rather easy because you can always look at the data, but this is sort of helping you to understand what we are doing. So suppose you have a one-dimensional function, which is this solid curve here, and you know the function only at random or selected instances. So here I have chosen these tj's to be random numbers between 0 and 1, and then I'm assuming that my data consists of these pairs tj, ftj. Okay, so you know those red points, and so you want to have an approximation of the function so that you can evaluate the function at any point, not only at those discrete points tj. So you want to do some sort of regression, and so of course in one-dimensional case you can do spline regression, you can do polynomial regression, whichever you want, because this is simple. In higher dimensions this is not possible, but this is simply to make it clear to you that what I'm trying to do here. So I want to find an approximation of the function based on the lacunary observation of the function at those red points. And moreover, I want to do it such a way that when I evaluate this function is a tree. So I want to approximate this solid curve here by a tree which is sort of fitting the function to those data points. And so what does it mean that the function is a tree? The idea is that, let me see, I will come to the what I mean by the tree soon. So suppose we have initial observations. So we have an interval, and then we know that the function is observed at points t1, t2, etc., tq. Now, suppose you, so this is any interval. So I'm starting to put together this tool. So suppose you have any interval, not necessarily the full interval from 0 to 1, but let's say interval from 0.4 to 0.6, for instance. So you have some points in that interval, and let's call t1 to tq the points where you know the function. Now I'm asking, what is the best constant m that approximates the function in the mean square sense in that interval? Well, by definition of the mean squares, you try to find the function m, the constant m, so that this mean square error Sm, which is defined here, is minimized. So what is m that minimizes the mean square error? Well, this should be easy to do. So you just take the derivative of S of m, and you write that this derivative is equal to 0. So that's the critical point, and it turns out that has to be the minimum. And when you do this calculation, which I leave for you to do, you realize that the best possible m is 1 over q, not m, so there should be a q here, that's a typo, times the sum j running from 1 to q of ftj. So that means that m is the mean value of the values that you have in that interval. So that is not surprising. That would be your guess probably if I would ask you what is the best approximation in the mean questions for the function. I think everybody would say, well, let's use the mean value, and that's indeed is the case. So it is the minimizer of this. Now, let's make it a little bit more complicated. Suppose I take this interval again, and I'm splitting in it two. So I'm taking a value s, and I'm splitting the interval in two subintervals, from t1 to s and from s to tq. So s is chosen to be a number which is not coinciding in any one of those numbers, t1 to tq. And so if I take this s from that interval, it falls between two t values. And so let's go tr, the last t value, which is less than s, and tr plus 1, the first one, which is above s. And so now I'm asking another question. So suppose I'm approximating my function by piecewise constant function, so that the function has a jump at s. So I'm allowing the function to have one constant value on the left part of the interval and another constant value on the right part of the interval. And so now I'm writing the mean square error, which depends on s, of course, where I have these two parameters, ml and mr. So these are the values to the left and to the right. So I'm approximating my function with a step function. I'm trying to fit the step values so that I have the least possible mean square error. So I'm trying to minimize it with fixed s. Now, I don't think it's a rocket science to guess that, again, the ml and mr have to be the mean value of the function values to the left or to the right of that division point. So that would be at least my guess, and indeed that is the case, because if I differentiate this function with respect to ml, this second term doesn't contribute, and so you are just calculating the derivative of the first one, and we already saw that the mean value is the best possible value, and so it's not a big surprise that the best possible value ml is the mean value to the left, and the mean value to the right is the best mr value. Notice that these values depend on s, because if I move my s, I get different values. right? So if I switch the S, so then this R may change, and so then you see that the mean values are going to change. And so therefore, if I'm asking what is the optimal split value, so where should I split so that I get so that my step function is the best possible approximation of my function. So then I should remember that this ML and MR are simply functions of S. And so now I have a function which depends on S. And so then I go and try to minimize this. Now this minimization looks a little bit more complicated because this may not be differentiable. Why is it not differentiable? When I'm moving my S, I'm suddenly changing the number of points which are falling to the left or to the right. And so there's a jump in the values of ML and MR. And so this function S here is no longer differentiable. But so since my number of data points is finite, as we did in the classification tree, you can always choose these S's to be discrete values between the data points. And so you have a finite number of discrete values, and you pick the one which gives you the minimum. And so that's the optimal split value. So now, if you want to grow a regression tree that approximates your function, that you know, so if you take any interval a, b, so you check which t values are in the interval, and then you compute the optimal constant approximation of the function, mean to the left and to the right, and you find the optimal split value. So you do this with all possible choices between these t values, and you generate a left and right offspring. So what do I mean here? So here is a function as a tree. So what does a function as a tree mean? So I have done this approximation now, and so suppose you give me a value t, and I'm asking what value my function takes on. So you give me a t between 0 and 1. What I'm doing, I'm I'm going through my tree. So I'm going to one of those intervals that I have in the current splitting, and I'm asking if t is smaller than the jth split value, and then I'm going down the tree to the left, and if t is larger than the split value, I'm going to the right of the tree. And so my function is now approximated by the mean value in the subinterval, and so if I stop the process there, then I have an approximation for the function, which is the mean value in the interval. Again, this may be a little bit obscure, so I believe that the best way to understand this is to look at what is happening here. So here is my tree, how it works. So the blue points are my data points, okay? So I start with the interval from 0 to 1. I'm looking all the data values here, and then I'm looking the optimal value S, where I split my interval, so that when I take the mean value to the left and mean value to the right, the mean square error is as small as possible. And when I do this, I'm testing all values between the data points, and I find that the best fit, that is the minimal least squares error, is obtained if I split along this dashed line here. And so now my first approximation of my function is the step function, constant to the left of that split value and constant to the right of that split value. Now I'm looking at those intervals, and I'm starting to go through the two intervals, and I'm continuing to split the intervals. So what I'm doing first, I'm taking this interval to the right, and I'm asking if I take only the values which are in this interval to the right, where should I split the interval so that piecewise constant approximation is the best possible approximation. And if I do this analysis, it suggests that there is a split value here, and so I'm splitting my function right there. And so now I have a two split situation. So if you give me a t, and I'm asking what approximation this tree would give me for the value of a function. So you give me a t, I'm asking first whether it's left to the right of the first split value. If it's to the left, I'm using this value. if it's to the right, I'm asking another question. Is it left or right to the second split value here? And then I'm using either this value or that value to approximate the function, and so on. And so I continue this splitting. I'm using an algorithm that I'm putting the leaves, you know, I have two kinds of leaves. Either the mean square value is 0 or it is not. And if it's 0, then I have so-called pure leaf and I don't split any longer. If I have a mixed leaf where the mean value is the mean square error is not yet constant, there is space for splitting and I continue splitting. And so you see how the splitting goes. I'm refining and refining. So here is 1, 2, 3, 4, 5, and 10 splits. So you already see that this piecewise constant function is approximating pretty well the function. And so this corresponds really a tree because I arrived to this approximation by asking questions left or right. And so I can really represent my function as a tree. And so then I continue, and after 35 splits, I get this pretty detailed piecewise constant approximation of the function. And so this is the final, or the, let's say, the tree regression of my function after 35 splits. You can continue. As you see, there are some intervals still that could be split, like this one here, where you have, I think, 4 values in this interval, but I stop here so that you see what is happening. So this is the strategy how you approximate the function as a tree. Well, in 1D, this is a really pretty boring procedure. But if you have, let's say, higher dimensional functions, this may be very useful. So suppose you have a 4-dimensional data space and you want to approximate the function in 4-dimensional data space. Having a simple way to evaluate the function using trees is really valuable, because these tree algorithms are very fast to compute. And so this, rather than trying to do a 4-dimensional spline regression, for instance, which may be less intuitive, you can always do this tree regression, and it gives a really fast way of approximating a function which you know only in some points. Okay. So we can look at a little bit more interesting questions. So one-dimensional signal is rather boring. So I made an example of sort of a challenging in-painting problem. So suppose you have a color image which is represented as an RGB image, so red, green, blue image. So each pixel Pij in this image contains a vector Vij, which is the R value, G value, and B value. So R, G, and B are numbers between 0 and 1. I have scaled my image colors in that way. And so then, if you have the RGB values, you can always plot the pixel with a given color, which is the RGB representation of the color using these values. Now, this is the image. And so if I have all the image, I just plot it using the RGB values, and that's it. But so now suppose that you have an in-painting problem. So suppose the image has been sent from Mars, from a probe, and for some reason the data has been corrupted severely. So you have only less than 1% of the data coming to you. And so an image is given, but less than 1% of the pixel values are given. And so you would like to see what the image is. So this is a sort of a challenging in-painting problem. So you try to make sense of an image where you have just less than 1% information left. And okay, so here is a picture. So I made an image which I'm not showing you yet what it is. So it is a 3648 by 2736 pixel image made with a cell phone, and I am retaining only 0.15% of the pixel. So the image, if you plot it, so I'm plotting the pixel values here, and you don't see anything because the pixels are so small. So let's take a small detail. So this is a 250 by 250 detail, and let's look at that detail. And so if you look carefully, you see small dots here. They look pretty much blue to my eye, at least. And so you would think that there is this part of the image probably is something which is bluish. But so you would like to see what this image is. And so, okay, so what you do? We do a regression. So we are trying to approximate the image as a tree. So what I do, I start. I'm partitioning the image into the left and right, or upper and lower rectangle, depending which one gives me a better fit. And so then I'm coloring the rectangle with the RGB by computing the mean value of the RGB values in both of those pixels. Okay, so I'm just dividing this pixel either with a horizontal cut or a vertical cut, and then I'm coloring the sides with the mean value. And then I'm continuing. So I'm taking one of those rectangles and I'm splitting again, and I'm coloring the sub rectangles with the mean value of those rectangles, and I continue this way. And I'm always trying to do the best possible split, in the sense that each split should cut the mean square error as strongly as possible, so that the mean square error is always minimized. So that gives you the optimal way of cutting the image, because we want the most economic way of representing the image, yet we would like to see what the image is. And so you continue splitting the rectangles. This is the maximal tree. So you continue splitting the rectangles until each rectangle contains only constant RGB vectors. And so that may lead to a huge tree, but so you can stop the cutting at some point. When you start already understanding what the image is, you can stop doing this cutting. But let's say ideally, if you want, you can go all the way to make sure that all the rectangles are leaves, meaning that the mean square error of each rectangle is 0. So I'm splitting my picture in two, left and right. So left and right means that I'm looking at one of the attributes, x coordinate or y coordinate. So I have the NL or NR. So there should be, this is a little bit of typo, so it should be NLR. In this sense, it is the number of pixels, and then you calculate the mean value of the RGB vectors in both, and you're minimizing. So here is the idea. So you're minimizing. So this one here is referring to that I'm cutting along the first coordinate axis. So I can also cut along to the second coordinate axis. And so then I'm looking the mean square error, which in this case is simply the pixel values minus the mean value over the left and over the right rectangles. And so then I calculate the same thing for all splits in the second direction. I'm choosing Sj for both of these j values to minimize the least square error. And if the least square error is smaller by splitting along the x-axis, I choose that one. Otherwise, I choose the y split. And so then you continue until the rectangles are pure. So this is a pretty straightforward algorithm. And so here is my mystery image. So this is the data. And so now I start cutting this image. And so it turns out that the best cut that I can do is along this first axis. So my first axis is the horizontal, the vertical, and second is the horizontal. So I'm thinking this in terms of a matrix. So the first index is a row index, and the second index is a column index. So therefore, my splits values are that way. And so this is the first approximation. So looking at that, you would think that there must be sky in the image and there is a horizon line somewhere there, but that's not very informative. So let's do the second split. The second split. So when I have four cuts, turns out that the upper rectangle is cut in here, and so there is this different shade of blue in those, and this which I believe is some sort of ground is cut in two. And so this is a fine game if you want to play games with people. So you can say, well, who guesses first what the image is wins. And so you can continue doing these splits, and you keep guessing what you have in the image. I'm not doing it with you, but I'm showing some reconstruction. So here are 20 leaves. So I jump a little bit forward. So now you start to see some green here. So maybe there is some sort of some grass. What is up here I don't really know, because the blue is no longer uniform. And so when I go to 500 leaves, you start to see that, oh, there's a lighthouse probably, and there's some sort of building here. And so then you go to 1,000 leaves, and you start to see the details of the house and the lighthouse. And here is 2,000 leaves. So remember what we started with. We had this awful black picture where I have only 0.15% of data available, and so you start to see what the image is. And so here is 300 leaves. And so we gave this to our students and asked them to figure out what it is. And one student said, well, it not only looks like a lighthouse, but it looks like a lighthouse that I know. And the student knew that this is really the what is it called, Cape Dove or something like that in California. So yes, so this is the original image, and this is the approximation using 3,000 leaves. So you see that this is a nice way of doing making sense of a strongly corrupt image. And so little by little, so you can stop the splitting whenever you want, and so that gives you an idea of what the image is, and so, but you can go all the way to this is not the last possible image. You can continue, and you also start to see a little bit of details of this picket fence if you do that. So surprisingly, there is enough information in 0.15% of pixels to make sense of this image, and so and so this is really a tree. So that's the interesting thing. I never thought that an image could be thought as a tree, but this corresponds to a tree structure. Okay, so that's basically the material that I was hoping to share with you, and so we are at the end of the lectures, and so before I stop, I will give you the let's say the final exam. So what the final exam is, I'm asking you to go to the web page of the textbook. If I manage, I will show you the page. So so this is the site, and so this is the site of the other author, Daniela Calvetti, who is keeping this data science book site. So if you go to the SciAm book page, I believe it guides you to this site too. So you don't have to know this book if you have the access of the Google site of the textbook. But since you have direct access to this, you can just go to this site. And so on this site, you will find a number of assignment sheets. And so I choose 3 topics that we have been discussing. And so I'm asking you to take a look at those problems. So there's one problem. I'm saying 1 and 2, but they are really related problems. So problem 1 is that I'm asking you to implement your own self-organizing map algorithm, and problem 2 is to apply to the handwritten digit image data, which we can also download from this site. So the data is available in MATLAB form on that site. So you can download the data, and problem 1 is to write your own code. If you want to use Python, I believe, let's see, this is a math file, so so you probably can save it in as a DAT file and read it also using other programs. So then there is one problem with non-negative matrix factorization, and this is a classic problem of separating sources. And then there is one problem with image mining where this is problems 1 to 5. So the one is that you create the grayscale co-occurrence matrix. I think 1 to 3 is just to construct the co-occurrence matrix and then apply the linear discriminant analysis to the data to see that the different textures that you can download from the page can be separated. And I thought that maybe 10 days would be a reasonable period of time to look at these problems. So if you send by June 13th your report to my email address, which is given here, I will look at your work. And so, as I said, the final will be graded as a pass-fail. So I'm not really going to give you detailed feedback. And what is a passing grade? Passing grade requires that I see that there is a serious effort for solving the problems, so that I can see that there is more than just downloading the data. Let's say so there's a serious effort to try to write the program, and the report should be self-explanatory. So please don't send me a computer code alone. I'm not going to run the computer codes. I want to see what the computer code is doing. And so that means that there should be some sort of self-explanatory report saying that I did this, this, and this is the result. Okay, so that's what I mean by self-explanatory report. So even a well-documented code is not a report, because in order to understand whether, first of all, that the code works and it does what it's supposed to do, would require me to go and run the code, and so that's not what I was planning to do. So you have to run the code, have the results, and include the results into your report. And I understand that there looks like there's a lot of things to do. So please do your best, and I try to be fair with the grading. So if I see that there is a serious effort for solving these problems, I believe that will be sufficient. And so with that, I'm finishing this course, and I show you this nice picture, which is also in the cover of the book. So now you see what it is. It's the Rock and Roll Hall of Fame from Cleveland, a nice building of INdAM, and you see that the lake here is solid frozen. So this is a wintertime picture. It's nice in the summertime too. Okay, so thank you for all. Let me see if I can share the page of the. I have a couple of minutes time, so if I can share the page of the book. I think this is it. Just a moment. All right, so let me try to share the screen with you again. Do you see the screen?
No, not yet.
Oh, you don't see it. Okay, so let me try again. Okay. Does it show now?
Yes.
Okay, great, good. So here's the book, and now you see the cover. So this is really the regression tree approximation of the nice building that I showed you. So if you go to the page, so you see that there are lots of homework, and so let me show one of the problems, the non-negative matrix approximation. Here's the SOM part. So here's non-negative matrix factorization. So if I click on this NMF here, you see that link to sound source data.mat appears. So if you click to that, you can download the data. And so what is the data? So here is the idea. So we have a room, a circular room, and so these green dots here, they are representing positions where you are registering a composite sound coming from 4 sources, 1, 2, 3, and 4. We know where they are. So the sound from source 1 is this oscillatory sound. In source 2 there's just a bang, and 3 there is a step function, and then again a periodic function. So you would like to separate those sources. So now the idea is that you can think that the registrations, so this is a multi-channel data, which is a weighted average of these functions here. And so then what you would like to do is to decompose the sum into linear combinations of 4 sources with different weights. And so that can be done using the non-negative matrix factorization. And when you do that, you get some sort of recovery of the signals. And so so what you need to do is you need to go to the non-negative matrix factorization lecture, and there is this algorithm, this multiplicative updating formula. So implement that. It's rather simple to implement, and then you apply it to the multi-channel data. So your data is at each time instance. So time is here running from 0 to 1000. So you have 1000 data vectors, and each element corresponds to the linear combination of these signals. And so then you're trying to approximate your data like W times H, and so W contains now the sound sources, and H is going to contain the coefficients that constitute your data. So doing this decomposition, you will find so this is how the data would be composed. So if you know the locations of the sources, you can do this. You can create this data. But so if you don't have the locations, you don't know what this matrix W is. So I stated wrongly. The signals are going to be in this H matrix. So there's going to be 4 signals. Okay. So if you read carefully, I believe this should be doable. So it's 4 o'clock, so I think I'm stopping here, and I thank everybody for participating into this course. It has been fun for me to teach this course, and I hope you have the feeling that you have some sort of general understanding of these data mining techniques that were covered in this course. So thanks everybody.
Sorry, Professor.
Ok.
I
Beh,
have a question.
grazie, arrivederci.
Grazie.
Erkki, grazie. Puoi restare 5 minuti perché mi hanno risposto dall'INdAM, dal GNCS, per vedere cosa devi fare per chiudere il corso. Quindi
Okay.
Quando gli altri si scollegano ti condivido il mio schermo e ti faccio vedere, poi ti inoltro la mail, va bene?
Ok, va bene.
I'm sorry, I have
Se
a
vuoi
question.
parliamo anche inglese, perché sono fatti tecnici, in italiano sono un po' scoccianti, insomma.
Vediamo come vanno le cose in italiano.
No, ma non c'è problema a parlare inglese, ovviamente, però in genere quando sono fatti formali gli italiani sono molto contorti. Okay.
Sì, è vero.
Aspettiamo che gli altri si scolleghino e poi Ciao Rosanna.
Ciao Erkki, ciao Daniela. Ciao, grazie Erkki, alla prossima.
Comunque grazie per aver accettato di fare questo corso, che secondo me è proprio un corso interessante, molto bello. Infatti a me dispiace di aver perso qualche lezione per colpa di altri impegni però non potevo non fare altre cose purtroppo.
No, quello capisco, sì, sì. Quando noi facciamo... Guarda,
in un'altra università sei obbligato, se hai degli altri impegni, ad andare. C'è qualcuno che ha alzato la mano e vorrebbe dire qualcosa. MR chi è?
Io, Maria Pia.
Ah, Maria Pia. Ciao Maria Pia.
Salve, Prof. I have a question for the Professor Somersalo. Actually, is a requirement because we are PhD students, and up to me, I am attending something like 4 courses, of which 3 are mandatory. So it's a little bit complicated for me to make a report for the 13th of June. And I think it's not a problem only for me.
Okay.
And maybe it could be better to have more time, if it's possible.
Yeah, so I will be traveling, but I probably can do that later too. So is that okay? I'm asking Daniela, would that be like acceptable to? So what is the timeline that you need to have the?
I don't know. Maria Pia should answer this question because Maria Pia, you are attending 3 classes.
Yeah.
If I understood correctly.
Yes. Maybe
do all the classes require a final test?
Yes, because they are courses of the PhD, and this year we have all mandatory courses with the final exam. So it's a little bit tough for us.
So how much time do you need?
I don't know, even 10 days more could be nice. I don't know. Other students, please talk, because everybody's on the same boat.
Yes, Maria, you're right. We have courses until July.
Okay.
Half July.
All right.
So I don't know.
Yeah. Okay. So I can postpone. So I don't need to do that, you know, in that period. So I can postpone also the deadline if that's the general sentiment. Yeah. So I could be flexible. My deadline was simply to, you know, make it somehow to avoid the situation that, you know, people forget what they learn in the course, and so it was more like keeping things compact. But I understand if this deadline is undue, so it's creating complications for me. It's okay to postpone the deadline too. So look, my deadline was kind of arbitrary. Usually, when I'm teaching the courses here, I at the end of the course, I usually give 10 days. So I was sort of using the same protocol, but of course, that in our class, our semester, the usual the 10 days are after the actual semester. So you are in a little bit different situation because you have the courses going on, right?
Yes. And I think that only us PhD students have to do the exam.
Okay. So is there a way to reach everybody? If I have a list of, you know, of the email addresses of people who are taking this course, it will be easy for me to communicate that I've given an extension. Or if everybody is present here who is going to take this course, I can give the extension right now. So
I don't know if everyone is here, but maybe I could write a message on the team and ask for the students who have to do the exam to write me their email, and I will send you all the list.
Yeah, that could be helpful, but I can also post on the team page, you know, new instructions. So maybe I'll do that. I will post in the, you know, in the. Well, let's do this way. I can take away the slides that I uploaded, and I change the deadline, and I upload a new set of slides so everybody sees the new deadline there. Would that be acceptable?
I think so.
Yeah. So.
Yes.
Okay.
Okay.
So
somebody there's somebody else that raised his or her hand. I don't see the name.
Yes, it's me. I just wanted
Who
to
are
ask,
you? Can you show up, please?
Oh, yes, just a moment. I don't know if you are not. Wait, you see me
Yes,
now?
yes.
Yes. Yes.
Hi.
Yes.
Hi.
So I'm sorry, maybe it's a stupid question. I saw from the chat that, like me, someone tried to download the files related to the problems, but it seems there are some problems with the file about NMF. We can't download it.
Oh. Okay, I'll check this. So you can't download it. So.
If I try to download that file, it opens the PDF, only the PDF.
Oh, I see. Okay, I'll check that. I'll check
Thank you.
Okay, so I will do that. Thanks for pointing this out. So yes.
Thank you so much for the course and for everything.
No,
Bye.
Bye. Thanks for pointing this out. Yeah. Okay. So let me check what the problems are, and so then I will also upload a new deadline. So is that okay? I'll do that.
Okay.
Yeah.
Thank you so much, Prof.
Erkki, if the other students have no more questions,